This is section 1 of A-level Physics, measurements and their errors. First up, we got scalar quantities. These quantities only have magnitude. These can include distance, area, speed, mass and energy. Next up, we have vector quantities. These have both magnitude and direction. These can include displacement, velocity, acceleration and force. For SI base units, we have mass, which we measure in kilograms, length, which we measure in meters, time, which is measured in seconds, current, which is measured in amps, temperature, which is measured in Kelvin, and amount of substance, which is measured in moles. So Kelvin, we use that instead of Celsius, as 0 represents the complete absence of thermal energy. So this means 0 degrees Celsius equals 273.15 Kelvin. For the derived units, we have 1 joule, which is equal to 1 kilogram meter squared per second squared, and 1 volt, which is equal to 1 kilogram meter squared per second cubed per amps. For 1 newton, we have 1 kilogram meters per second squared. For unit prefixes, we start at 10 to the power 0. If we want to go down, we can say centi, milli, micro, nano, pico, femto. Centi is 10 to the power of negative 2, milli is 10 to the power of negative 3, micro is 10 to the power of negative 6, nano is 10 to the power of negative 9, pico is 10 to the power of negative 12, and femto is 10 to the power of negative 15. And 10 to the power 0, if we want to go up from there, we can use kilo, mega, giga, and tera. So kilo is 10 to the power of 3, mega is 10 to the power of 6, and giga is 10 to the power of 9, tera is 10 to the power of 12. So an example could be 1 electron volt is equal to 1.6 times 10 to the power of negative 19 joules. So what is 1 mega electron volt? That would be 1.6 times 10 to the power of negative 13 joules. So next up we got errors. So when looking at errors, we either have random errors or systematic errors. So random errors are varying measurements due to unpredictable circumstances. To reduce errors, we repeat the method 3 times, then calculate the mean, or use computers to reduce human errors, or even use appropriate equipment. And we also have systematic errors. These are when measurements differ from the true value. To reduce these errors, we can calibrate apparatus by measuring known value, correct the background radiation, or read meniscus at eye level. For definitions, we have accuracy, so that is how close a measurement is from the true value. Precision is how close the measurements are from each other. Repeatable, when the original experiment repeats the investigation using the same method and equipment, obtaining the same result. Reproducible, when somebody else repeats the investigation. Resolution, the smallest change in a quantity being measured. For uncertainties, we have absolute, fractional and percentage uncertainties. So what is an uncertainty? An uncertainty is a range within where the true value lies. An absolute uncertainty is plus or minus half the smallest division. Fractional uncertainty is absolute uncertainty over the measured value. Percentage uncertainty is the fractional uncertainty times 100. To combine these uncertainties, if we are using addition or subtraction, we add the absolute uncertainty. If we are multiplying or dividing by these uncertainties, we are adding the percentage uncertainties. If we want to find the power of the uncertainty, we do the percentage uncertainty times n. When looking at graph uncertainties, to find the uncertainty in a gradient, we can use the best gradient minus the worst gradient over the best gradient times 100. To find the uncertainty in a y-intercept, we can use the best y-intercept minus the worst y-intercept over the best y-intercept times 100. The best just means the best line of best fit, which passes as close to the points as possible, and the worst is the worst line of best fit, either the steepest possible or the shallowest possible line which fits within the error bars.